Hold a slinky in the air, let it go, and something strange happens. The top starts falling exactly when you'd expect, but the bottom just hangs there, frozen in midair for almost a full second. It's not a trick, and the reason reveals something surprisingly deep about how nature works. Here's the setup. You're holding the slinky fully stretched. Zoom in on the bottom coil. Gravity pulls it down. The spring above pulls it up with the same force. Net force, 0. So here's the puzzle. When you release the top, why does the bottom keep hanging there as if nothing has changed? Here's the key insight. The spring is not rigid. When you let go of the top, the news of that release has to physically travel down the spring, coil by coil, as a compression wave. The top collapses first, squeezing the coil below it, which squeezes the next one, and so on. But until that wave reaches any given coil, that coil still feels the same upward pull from above. Nothing has changed for it yet, so it stays in equilibrium. For a real slinky, the wave moves at only a few meters per second, slow enough that the bottom can levitate for roughly half a second before the signal arrives. Let's put numbers on this. The speed of a wave on a spring is the square root of tension over mass per unit length. For a slinky hanging under its own weight, that works out to about root GL over 2. Plug in a 2-meter slinky, and you get a wave speed of around 3 meters per second, which means a travel time of roughly 0.6 of a second. That matches slow-motion video almost exactly. Here's where it gets beautiful. This isn't just about slinkies. Every physical signal in the universe travels at a finite speed. Pluck a guitar string. The vibration races along at a few hundred meters per second. Tug on a long rope, the far end doesn't move until a tension wave reaches it. Even light itself is a wave, and its speed is the ultimate limit. The slinky is just a slow-motion version of a rule baked into every physical interaction. Your turn. Imagine you used a slinky with twice the mass, same length, same spring constant. What happens to the hang time? The answer is B. It stays exactly the same. Doubling the mass doubles the tension, because tension is just weight. But it also doubles the mass per unit length. The two cancel. Wave speed unchanged. Hang time unchanged. A perfectly counterintuitive result. A slinky falling isn't really a toy. It's a slow-motion demonstration of one of the deepest rules in physics. Information takes time.